Secure Communications Interoperability Protocol. The Secure Communications Interoperability Protocol (SCIP) is a U.S. standard for secure voice and data communication for circuit-switched one-to-one connections, not packet-switched networks. SCIP derived from the U.S. government Future Narrowband Digital Terminal (FNBDT) project. SCIP supports a number of different modes, including national and multinational modes which employ different cryptography. Many nations and industries develop SCIP devices to support the multinational and national modes of SCIP. SCIP has to operate over the wide variety of communication systems, including commercial landline telephone, military radios, communication satellites, voice over IP, and the several different cellular telephone standards. Therefore, it was designed to make no assumptions about the underlying channel other than a minimum bandwidth of 2400 Hz. It is similar to a dial-up modem in that once a connection is made, two SCIP phones first negotiate the parameters they need. US SCIP or FNBDT systems were used since 2001, beginning with the Condor's secure cell phone. The standard is designed to cover wideband, as well as narrowband voice and data security. SCIP was designed by the Department of Defense Digital Voice Processor Consortium (DDVPC) in cooperation with the U.S. National Security Agency and is intended to solve problems with earlier NSA encryption systems for voice, including STU Roman 3 and Secure Terminal Equipment (ST), which made assumptions about the underlying communication systems that prevented interoperability. ST sets can be upgraded to work with SCIP, but STU Roman 3 cannot. This has led to some resistance since various government agencies already own over 350,000 STU Roman 3 telephones at a cost of several $1,000s each. There are several components to the SCIP standard: key management, voice compression, encryption, and a signaling plan for voice, data, and multimedia applications. Key management 120. To set up a secure call, a new traffic encryption key (TK) must be negotiated. For Type 1 security classified calls, the SCIP signaling plan uses an enhanced Firefly messaging system for key exchange. Firefly is an NSA key management system based on public key cryptography. At least one commercial-grade implementation uses Diffie-Hellman key exchange. ST use security tokens to limit use of the secure voice capability to authorized users, while other SCIP devices only require a PIN code, 7 digits for Type 1 security, 4 digits for unclassified. Voice compression using voice coders, vocoders. SCIP can work with a variety of vocoders. The standard requires as a minimum support for the mixed excitation, linear prediction MELP coder, an enhanced MELP algorithm known as MELP, with additional preprocessing, analyzer, and synthesizer capabilities for improved intelligibility and noise robustness. The old MELP and the new MELP are interoperable and both operate at 2400-bit/s, sending a 54-bit data frame every 22.5 milliseconds, but the MELP has optional additional rates of 1200-bit/s and 600-bit/s. 2400-bit/s MELP is the only mandatory voice coder required for SCIP. Other voice coders can be supported in terminals. These can be used if all terminals involved in the call support the same coder agreed during the negotiation stage of call setup, and the network can support the required throughput. G729D is the most widely supported non-mandatory voice coder in SCIP terminals, as it offers a good compromise between higher voice quality without dramatically increasing the required throughput. Encryption SCIP-23. The security used by the multinational and national modes of SCIP is defined by the SCIP-23 family of documents. SCIP-231 defines AES-based cryptography, which can be used multinationally. SCIP-232 defines an alternate multinational cryptographic solution. Several nations have defined, or are defining, their own national security modes for SCIP. U.S. National Mode SCIP-230. SCIP-230 defines the cryptography of the U.S. national mode of SCIP. The rest of this section refers to SCIP-230. For security, SCIP uses a block cipher operating in counter mode. A new traffic encryption key TK is negotiated for each call. The block cipher is fed 64-bit state vector SV as input. If the cipher's block size is longer than 64 bits, a fixed filler is added. The output from the block cipher is XORed with the MELC data frames to create the cipher text that is then transmitted. The low-order 2 bits of the state vector are reserved for applications where the data frame is longer than the block cipher output. The next 42 bits are the counter. 4 bits are used to represent the transmission mode. This allows more than one mode, e.g. voice and data, to operate at the same time with the same TK. The high-order 16 bits are a sender ID. This allows multiple senders on a single channel to all use the same TK. Note that since overall SCIP encryption is effectively a stream cipher, it is essential that the same state vector value never be used twice for a given TK. At MELC data rates, a 42-bit counter allows a call over 3,000 years long before the encryption repeats. For Type 1 security, SCIP uses Baton, a 128-bit block design. With this or other 128-bit ciphers, at least one commercial-grade implementation uses the triple DS cipher. Signaling Plan 210. The SCIP signaling plan is common to all national and multinational modes of SCIP. SCIP has two mandatory types of transmission. The mandatory data service uses an ARQ protocol with forward error correction (FEC) to ensure reliable transmission. The receiving station acknowledges accurate receipt of data blocks and can ask for a block to be retransmitted, if necessary. For voice, SCIP simply sends a stream of voice data frames, typically MELC frames, but possibly G729D or another codec if that has been negotiated between the terminals. To save power on voice calls, SCIP stops sending if there is no speech input. A synchronization block is sent roughly twice a second in place of a data frame. The low-order 14 bits of the encryption counter are sent with every sync block. The 14 bits are enough to cover a fade out of more than 6 minutes. Part of the rest of the state vector are sent as well, so that with receipt of 3 sync blocks, the entire state vector is recovered. This handles longer fades and allows a station with the proper TK to join a multi-station net and be synchronized within 1.5 seconds. Availability. As of March 2011, a range of SCIP documents, including the SCIP-210 signaling standard, are publicly available from the IAD website. Prior to this, SCIP specifications were not widely diffused or easily accessible. This made the protocol for government use rather opaque outside governments or defense industries. No public implementation of the Type 1 security and transport protocols are available, precluding its security from being publicly verified.